Hello and good day. This specific video lecture would cover the following topics. So we'll look into the computation of frequency given the period and vice versa, as well as the determination of wavelength given the frequency and vice versa as well. Then we will be proceeding with computation of bandwidth or the bandwidth of a signal. And then finally, we'll be looking into gain or the computation of gain and attenuation and the use of decibels. But before we begin with the lesson proper, we will need to have a bit of understanding on how to compute using what we call engineering notation. This is essential as most, if not all, computations involving the metric system are shown using the engineering notation. So we will begin first with what we call the scientific notation, and then we will proceed with engineering notation. So let me give you an example on how we will be able to convert specific values into the engineering notation. So let's have 5 examples here. So let's say we have the following values. So let's say this is 3,500 volts. Let's say this is 0.00013 amperes. Number 3 would be let's say 1,200,000 watts. Let's also have 0.15 seconds. And finally, let's have 700 bytes. So when we are about to convert this into engineering notation, what we have to do first, for example, we have number 1. Let's isolate number 1 here. I'm going to put it somewhere below rather. So we'll put our final answers at the top. So let's say we have 3,500 volts, and we are going to convert it into engineering notation. So what we do first is we actually move the decimal place up until the number of digits is 3 or less. Right now, there are 4 digits representing the value. So 1, 2, 3, and 4. That would include zeros. So we would be converting to engineering notation if it is greater than 3. So because we have 4 digits here, we need to convert this into engineering notation. So how do we do that? We have a decimal point here, but of course with whole numbers we do not show it anymore. We only show it if it has like a fractional part. So what we actually do is we move our decimal point 3 times to the left. Okay, so it will always be in multiples of 3. So in this case, we will move it 1, 2, and 3. So what would happen is that the decimal point from this position would now go to this position, making our value equal to 3.5, right? Because it was 3,500 before, we move it 3 times to the left, it now becomes 3.5. Now, how do we know that we would stop or we would continue moving the decimal point? If the whole number part only has a single, 2, or 3 digits left, then we stop with moving the decimal point. So in this case, we only have one whole number or one digit for the whole number, which is 3. So we already stop. Now, of course, 3,500 is not the same as 3.5. So how do we make sure that these are still equal? So we use our exponent, which would be times 10. And then it would have an exponent here equal to the number of digits we skip. So in this case, we move it 3 times to the left. So we put in positive 3. And then we put in the unit. Okay? So we always do that. Again, we have 3,500. It's composed of 4 digits. If we want to move it into engineering notation, we only want at least a single, 2 or 3 digits. So we move the decimal point from here 3 times to the left, so always in multiples of 3. It becomes 3.5. We stop because there's only one whole number left. Then we put in times 10 raised to 3. The times 10 is consistent or constant. The only thing that would change is the exponent. The 3 here comes from the number of number of digits I move our decimal point to. Okay. So it's now to the third, and then we don't forget to write the unit. So if it's volts, we always write the volts here. Okay. So let's write our answer at the top. This is not yet the engineering notation, but this is the beginning of the engineering notation. So 3.5 times 10 to the 3 volts. Okay. So 3.5 times 10 to the 3 volts, we will now convert it into our engineering notation. So how do we do that? We look at our times 10 to the 3 right here, and then we look at our table, and times 10 to the 3 is actually kilo, which is denoted by the small letter K. So this is times 10 to the 3 right here, and we use K as a symbol. So how do you write that? We still write the number 3.5. Okay. And then we have the times 10 to the 3, which is equal to kilo. Instead of using this prefix, we use this. So we put in K here. And then volts. So this would now be the engineering notation. 3.5 kilovolts. Let's go on to the next number, which is 0.00013 amperes. So let's write it down here. So 0.00013 amperes. Okay. This time it's a very, very small number. Now if you look at the left side, you might be thinking that, oh, we only have one whole number on the left, so we won't be converting this into engineering notation. But when converting to engineering notation, we also look at the number of the decimal places. If there's no whole number, let's say that is 0, the next step would be to look at the decimal places. So right now, we have 1, 2, 3, 4, 5 digits on the fractional side. As mentioned, in engineering notation, we only want 1, 2, or 3 digits. So how do we do that? So this time around, because there's no whole number on the left side, instead of moving this to the left, we move the decimal point to the right. Again, in multiples of 3. So 1, 2, 3. So it has now become 0.13. So we will rewrite this as 0.13. Okay. Now, is this done? Not yet. Although we have only two decimal digits in here, we need at least 1, 2, or 3 on the left side. That is why we would still move this another 3 parts. So we'll be removing this just to show. We just written that to show that we need at least a whole number. Single, 2, or 3 digits. So we move 3 again. So 1, 2. Now you will notice that there's no digit here. How can we move it another space? Well, we can, because technically speaking, there is 0 here. So if we are lacking digits when we are moving this 3 to the left, or to the right rather, we actually add a 0 to compensate for the missing digit. So what would happen is that from here, we move it 3 to the right. No whole number. We move again 3 to the right. There's no digit here. We added 0 to make sure that it was able to move in 3 times. So it will now become 130. Okay. But how do we compensate with the number of digits? Again, the times 10 is constant. And how many digits did we skip? Or how many times did we jump? So 1, 2, 3, 4, 5, 6. So we will now have 6 digits. 1, 2, 3, 4, 5, and then 6 digits. And the 6 digits, we put in the number 6. Now, after the 6 digits, because we moved this 3 times to the right, we put in a negative sign. So that's the difference between moving the decimal number from left or to the right. Since for the first example, we moved the decimal point to the left, we put in a positive 3. If we are moving it to the right, then we put in negative number. So this is 6 times, and it is to the right, we put in negative. And then we don't want to forget the amperes. Okay? So let's just write it down for our reference. So this would become 130 times 10 to the negative 6 amperes. So we look at our table, the times 10 to, we look at the times 10 to the negative 6. We write the 130 first, as always. And the times 10 to the negative 6 is micro. And it is denoted by the Greek letter mu. So why aren't we using m? Because we already have an m for milli. So we can't use another m. So what we're going to use is the Greek letter for m, which is mu. So this is just like the you call this the shorthand or the cursive for the letter U. So we'll write that like this. Okay. And then we write the unit. So we write it as 130 micro amperes. So we have 3.5 kilovolts and then 130 microamperes. Let's try our next example. Let's do it a bit faster this time. So we have 1,200,000 watts. So we will be moving this number of bits to the left. So how many digits do we have at the left? So 1, 2, 3, 4, 5, 6, 7. Again, we only need 1, 2, or 3 whole numbers. So we move 3 times. 1, 2, 3. Not enough. We still have 4. We move another 3. 1, 2, 3. Now we only have a single digit and the whole number. So we'll put in 1.2. So 1, 2, 3, 1, 2, 3. Until only 1, 2, or 3 digits are left on the whole number side. We write in the times 10 as always. And then we write down the number of digits we skip. So 1, 2, 3, 4, 5, 6. So would it be positive or negative? Since we jump to the left 6 times, then it would be positive. Then we write the unit, which is watts. Then we convert it into the unit of power. And times 10 to the 6 here is the big letter M. So be careful with the big letter M. It is supposed to be mega. The small letter m is milli. And we use the Greek letter mu for micro. So in this case, mega, which is times 10 to the 6. So mega would be our replacement for times 10 to the 6. And the watts. Okay, so this would now be our converted 1.2 mega watts. So let's move on to our fourth example. Let's have a look. So let's have a look at 0.15 seconds. So we will now convert this into engineering notation. So right now this has no whole number digits here. So 0 is not counted if it's the only one there. So we need to move this 3 steps to the right. So this would be 1, 2, and then 3. As always, we compensate the number 0 here to be able to determine our missing digit. As if we move 3 times to the right, there's still a missing digit here. So this would now become 150. Okay, don't forget the times 10. Then 1, 2, 3. Okay. So this would be times 10 to the 3. Would it be positive or negative? Since we move to the right, 1, 2, 3, then we would be negative. Okay? And then we write the seconds here. Okay. Now, we're going to convert this into our engineering notation. Looking at our table, times 10 to the negative 3 is actually milli. So we'll replace times 10 to the negative 3 with a small letter m. So 150 m s. For seconds, sometimes they use SECS as an abbreviation. But in some cases, or in most cases rather, they just use the small letter s. So this is in seconds. 150 milliseconds. Let's go to our last example and take a look at how we will be converting this into engineering notation. So we have 700 bytes. Now, if you look at the number of whole numbers, 1, 2, and 3, it already has successfully fulfilled the conditions in which we only need 1, 2, or 3 whole numbers. So there are 3 here, 7, 0, and 0. I said a while ago that we don't include 0 if it is the only digit there, like this one and this. Since there's another digit here, these 2 are included. So there's actually 3 digits here. So 1, 2, and 3. So what do we do then? So if there are already only 1, 2, or 3 whole number digits, we don't do anything. We put it as is. So this is already good. So 700 bytes, we don't need to convert this whatsoever. I would like you to try answering this as your practice. So I'll write another number here. And let's see if you're able to understand our example. This is essential. We need to be able to understand the engineering notation before we actually go into the discussion of frequency, wavelength, and bandwidth. So let's say we have the following values. Let's say we have 37,500 meters, 0.02 seconds. So this is S. Oops, let me erase that. 0.000119 seconds. Okay. Next, let's have 13,500,000 bytes. Then let's have a very small number, 0.00000038 farad. Okay. And the last one, let's have let's have 30, not 30 again, let's have a different number, 89,000 ohms. So this is a unit of ohms. So I want you to take a look at this numbers. Try to look into converting this into engineering notation. I'll just pause the video and then we can go on to the next part of our discussion, which is about frequency, wavelength, and bandwidth. Now that we are done and know already how to use engineering notation, so it's time to know or learn about frequency, wavelength, and bandwidth. As mentioned in our online discussion, frequency is the number of cycles per second, or how many times a certain pattern in a wave repeats in a single second. So in order to get frequency, we need to be able to have the period. Period is the amount of time that a single cycle lasts or a single pattern lasts. So time is given in seconds, and frequency is given in hertz. In older times, it was given as cycles per second or CPS. So let's have a few examples here in which we have periods and then we want to convert it into frequency. So usually with frequency, the our time are given in as much very are in a very small value. So let's say we have the 0.1 seconds. Then let's have 30 milliseconds. Period in 100 microseconds. And a period in, let's have something very small, let's say 50 nanoseconds. Okay? So how do we determine the period for this or the frequency for this? So for frequency, okay, as mentioned here, it is 1 over period. So we'll have here 0.01 seconds. Okay. So after getting 0.01 seconds, we'll now look into using our calculator. So it is a requirement that you have your own calculator. If this was a normal class, but we have many applications and online calculator apps that we could use as a replacement. So I'll be using my calculator emulator here. Just a moment. So let me just run a Casio calculator here. Okay. So we will have let's remove the seconds as it looks like the number 5, so 0.01. We don't need to convert this yet to engineering notation. We just need the answer. And then if the answer needs conversion to engineering notation, that would be the time to convert it to engineering notation. So we'll have 1 divided by 0.01. So we'll have 100 as the answer. And then 100 is in hertz. Okay? So the unit for frequency is always hertz. Don't forget about that. So this would be the answer for our first question. Now let's have number 2. So for number 2, we're looking for the frequency of 30 or for a period of 30 milliseconds. So for 30 milliseconds, if we tried putting this into the calculator, 1 divided by 30, then we will get an incorrect answer. Because remember, the 30 milliseconds here is actually in engineering notation. So we have to convert it back into its proper notation. So this would become 1 over 30, okay, times 10. Now, if we look at the table, milliseconds is negative 3. So milli is negative 3. So negative 3 here. Okay. So how do we put that in the calculator? If you have this normal calculator or any other calculator, this is how we enter it. So we put in 1 divided by 30. Then this is the one that we used for times 10. So we just put this here. And then we can put in negative 3 automatically. Okay? We don't use time, we don't manually put in times, then 10, then exponent. Okay? So we could use this as our exponent already. Again, let us try that again. So we have 1, just this one, divided by 30. Then we put in times 10 to the x, and then which is representing this one, and then negative 3. So we'll get an answer of 100 over 3. Some calculators will show this instead, but we want to put it into engineering notation. Okay, so we just click ENG, and it will show us 33.33. So this ENG here is actually for engineering notation, and you only click it once. Okay, if you click it multiple times, it will change the answer. So that would be wrong. So let me have that again. The answer is 100 over 3. Click engineering notation once, and this is our answer. When writing answers with quite long decimal parts or fractional parts, we round off to the nearest tenths or the nearest second digit. So we have 2 here. So I'm assuming you know how to round off numbers. So this would become 3. So 33.33. Now, what would be the unit? Of course, this is in frequency. That shouldn't be a question. The answer would always be in hertz. So this would be the answer for our second problem. Next, we have 100 microseconds. Let's write that up. So number 3, we're trying to look for frequency. Just 1 divided by 100 microseconds. Okay. So we have to rewrite the microseconds, the 100 microseconds. So micro, if we look at our table here, is 10 to the negative 6. So we have to, it is here, 10 to the negative 6. So we write that here. Okay. So we write the 100 first. So 100 times 10 to negative 6. Okay. And that is what we will put into our calculators. So let's clear this first. So we have 1 divided by, let's write in the 100, then x10 raised to negative 6 is x10 raised x, then we type in negative 6. Again, 1 divided by 100, then x10 negative 6, this is our times 10 raised to x, then we type in negative 6. So this would be equal to 10,000. We click ENG once so that you won't have a hard time of converting it into engineering notation. So it's already 10 times 10 to the 3. So just write in 10 times 10 to the 3 hertz. We already know what times 10 to the 3 is. Okay. If you don't, let's look at the table. 10 to the 3 is kilo. Okay. So 10 to the 3 is kilo. So we write in, oops, almost erase that, 10, then this is K, kilohertz, and that would be our answer. Let's take a look at the last example. So let's take a look at our last example. So for number 4, we are finding frequency from 50 nanoseconds. So our frequency is now 1 over periods. In this case, it's 50 nanoseconds. And if you look at the table, nanoseconds is actually, oops, -9. So nano is times 10 to the -9. So let's write that up. Times 10 to the -9. Okay. Let's use our calculators. So 1 divided by 50 times 10 raised to x -9. And that would be equal to this number. Let's just click E and G once. And we get 20 times 10 to the 6. So 20 times 10 to the 6 hertz. And if you look at our table, once again, if you haven't memorized it by now, times 10 to the 6 is actually mega, denoted by the big letter M. Okay, let's put a box on this one. And there you have it. That this is how we convert or refine frequency if the period is given. Okay? Now let's move on to getting frequency from the wavelength and vice versa. So frequency again is the number of cycles per second. Period is how long a single cycle lasts. While wavelength, as mentioned in the discussion from last time, is the distance from one point of the wave to the next point or the same point on the next wave. Okay? And one thing you should note is that wavelength is inversely proportional to frequency. So the higher the frequency, the shorter the wavelength, and vice versa. So let's move on to the formula and determine the units involved here. So we already know that frequency is in hertz. But lambda, by the way, this inverted y is Greek letter for lambda. And this is the unit used to represent wavelength. Its unit is in meters. Okay. So how about letter C? So what is C? C is a constant, and this is actually the speed of light. Okay. Which is equal to 300 million. Meters per second. Or, if you want, you can just put it in scientific notation, 3 times 10 to the 8 meters per second. It's up to you what you want to use. Their formula is almost the same as for frequency. It's just that instead of having 1 at the top, you have c, which is equal to the speed of light. So it'll be a bit complicated compared to what we had a while ago, but not relatively or not really that hard if you think about it. So let's have 4 examples. 2 examples of converting or getting wavelength from the frequency. So let's have a frequency of 35 kilohertz to wavelength, and then let's have 150 megahertz to wavelength as well. And let's have an example for the opposite. For the first 2 examples, the given was frequency, we get the wavelength. This time around, let's get we have the wavelength. Okay. Let's have the frequency. So let's say we have 10 millimeters. Then we'll get the frequency. And let's have 250 meters, and then we're about to look for frequency. Okay, so we have 2 examples of each. Let's take a look at how we will be solving this. So let's say we have 35 kilohertz. So for number 1, so we have 35 kilohertz, and we are to get the wavelength. So wavelength from the formula is equal to c, the speed of light. Let's write that as 3 times 10 to the 8. Let's not put the unit anymore. You just have to remember that this is speed, so it is meters per second. And then let's write the given, which is 35 kilohertz here. Now kilo is times 10 to the 3. Okay. Remember that this is 35 times 10 to the 3 hertz. Okay. So let's use our calculator, handy dandy calculator once again. Let's just move this a bit to the left. Then let's move this to the right. So we have the 3 times 10 to the 8. So that is 3. Let's clear everything up. So 3 times 10 to the x, or exponent 8. So that's 3 times 10 to the 8. Divided by 35 exponent 3. So again, we have 3 exponent 8 divided by 35 exponent 3. Okay? So this is the 3 times 10 to the 8, and this is the 35 exponent 3. So the answer will be this. Then we just click ENG. So the answer would be 8.57. So we only use 2 decimal digits. And then this is 1. So 8.57. What would be the unit? Let me take a look at the answer. It's times 10 to the 3. Okay. Hertz. Meters rather, sorry. Because this is wavelength, I forgot. So this would be 3 times 10 to the 3 meters, which is equal to 8.57 times 10 to the 3 from the table is kilo. So kilometers. So 8.57 kilometers. Next, let's go to the second question. So the second question, we have 150 megahertz. So 150 megahertz. Convert this first into, we're still having problems with engineering notation. Convert this first into the exponential notation. So we'll have 150 mega. If you look at the table, it's times 10 to the 6 hertz. We are to use the same formula. The 3 times 10 to the 8 is a constant. We won't be doing anything there. And we just write in the 150 times 10 to the 6 at the bottom. And then our answer, let's look at our calculator. Clear this up. So 3 exponent 8 for the top portion, or the numerator. Then for the denominator, divided by, it's 150. So 150 times 10x times 10x to the 6. So the 6. And this would be equal to 2. So the unit is in meters. So you don't have to put this into engineering notation, as this is already, remember, if we have just 1, 2, or 3 whole numbers, then we're all set. And then don't forget the unit, which is in meters. So this would be our answer. Now, how do we solve for number 3 and number 4? What we have here is the formula for wavelength, C over F, which we use for examples 1 and 2. Well, it's actually quite easy because we just have to interchange frequency and wavelength here. So frequency would just be C over lambda. Just use algebra, then you'll get to this equation as well. So it's almost it's the same. So we don't have to worry about it that much. Let's look at our third example. 10 millimeters to frequency. So the wavelength given is 10 millimeters. Okay? 10 millimeters, let's convert that into exponential notation. Times 10 milli from the table is negative 3. Then meters. We use the formula. It's 3 times 10 to the 8, which is our speed of light, divided by time times 10 to the negative 3. And then we have, use our calculator again. Oops. Let's move this to the left. So we have 3 exponent 8 divided by 10, the exponent negative 3. Then equal sign, ENG, that is 30 times 10 to the 9. And times 10 to the 9 is giga. 30 times 10 to the 9. And because we're looking for frequency, this is in hertz. So our answer would be 30 gigahertz. Okay. So let's look at the last example, 250 meters to frequency. So number 4. Now the good thing about this problem is that this is already in standard notation, as we only have 3 digits and this does not have a prefix. Okay, so we can put this as is in our equation, which is of course speed of light, 3 times 10 to the 8 divided by 250. No exponents needed, as this is only 3 digits for the whole number. Calculator again. 3 exponent 8 divided by 250. So this would be equal to, I forgot to click ENG. So 1.2 times 10 to the 6. And we are looking for frequency, so definitely this would be in hertz. And times 10 to the 6 is mega. So 1.2 megahertz would be our final answer. The last part for this discussion, or for this part rather, the last part for this part would be getting bandwidth for a certain signal, channel, or whatnot. It's actually quite easy. Just subtract the higher frequency, or you just subtract upper frequency minus lower frequency. That's it. So if we're given a channel, or we're given a station, given two frequencies, we just subtract the lower from the higher. So upper minus lower, okay? And of course, bandwidth contains frequency, so the unit is still in hertz. I'll just give a few examples, just give two. So let's say we have two frequencies. F1 would be 30 kilohertz, and the other one, F2, is in 15 kilohertz. So it's just as easy as the larger, so bandwidth is just the higher, 30 kilohertz minus 15 kilohertz. Okay. So 30 minus 15 is 15, and then we just use the unit, which is kilohertz, and this would be our answer. Now we can only subtract frequencies directly if they have the same prefix. So for example, if we have something like 1 megahertz as one of the unit, F1, and then our second is something like 900 kilohertz. Unfortunately, we cannot subtract this directly. Yeah? So what do? So we transform this first into its equivalent notation, which is 1 times 10 to the 6 hertz. It's times 10 to the 6 because it is mega. And this one would be 900 times 10 to the 3, because kilo, or K, is times 10 to the 3 hertz. Then you subtract the larger from the smaller. This is larger because this is mega. Okay, and this is times 10 to the 6. So we have 1 times 10 to the 6 minus 900 times 10 to the 3. Be careful with subtracting this, as you might think this is the larger one, as this has 900 and this is only 1. Take a look at the unit first, or the exponent first. Again, we need not convert this into its standard form, as they are both in kilohertz, so we can subtract them directly. But these two are not. Mega and kilo are different. Use your calculator if you need to. So 1 exponent 6 minus 900 exponent 3, which is equal to this one. Click ENG, and then you get 100 times 10 to the 3. So 100 times 10 to the 3. And the unit here is hertz. As this is, bandwidth is still frequency. Convert it back to our engineering notation. Times 10 to the 3 is of course kilo, and then hertz. And there we have it. So we're done with the second part of our discussion, which is about the frequency, wavelength, and bandwidth. We'll now go to the last part, in which we need to determine the gain and attenuation in its absolute value, and also show it in decibels as well. Before we go to the lecture of getting the gains and attenuation in absolute value and decibels, let's have a practice session first if you truly understand how to get frequency, wavelength, and bandwidth. So I'll give you a few questions that you need to answer and see if you'll be able to get the correct answer. Oops, I made a boo-boo right here. Let me just move this a bit to the left. So convert this into what is needed. So for number one, get the frequency given a period of 30 milliseconds. Number two, get wavelength given a frequency of 35 megahertz. Why am I always writing 35? Let me get a different value here. Let's have, I don't know, 47. Yes, 47 megahertz. Let's reverse that one. Another frequency. So get the frequency given a wavelength of what's this, 47 frequency, so let's have a wavelength of around 55 millimeters. And finally, for number 4, this is a bit easy. I want you to get the bandwidth. Okay. For a value, or for two frequencies having, one having 500 kilohertz and the other one having 300 kilohertz. Okay. So try to solve this and go ahead and check if you got the correct answer. Then, let's go now to our discussion of gains, attenuation, and converting it into decibels. Now, let us continue with our discussion. So, this will be the last part, which is about getting the gain and attenuation and decibels. So, when we talk about gain, what we're talking about is how much the output has become compared to the input. If it has become larger as compared to the input, it means it's gain. But if it is lesser than the input, that means we call it as loss or attenuation. Again, if it was amplified, it became larger compared to the input, then it is gain. If it is lesser or there was loss, we call it as attenuation. Technically speaking, gain and attenuation is denoted by a big letter A. And gain or attenuation is determined by dividing the output over the input. You can only divide units, or you can only divide values having the same units. So usually when we look at gain and attenuation, we look at either voltage over voltage, current over current, or power over power. So let's have a few examples to show you how do we compute gain. So for example, let's use a red ball pen here. Let's have number 1, 2, 3. Okay. Again, it is supposed to be output over input. So normally, for voltage, you will see something like V in for the input and then V out. That is how you signify, or usually signify, inputs and outputs. Okay. So let's say the voltage input is 35 volts and the V out is around, let's say, 140 volts. Okay. For number 2, let's have the input current as 20 milliamperes and our output, let's say, is 5 milliamperes. Now let's say our power input is around 35 kilowatts, and let's say our power output is around, let's change this to a different value. Let's say this is around 100 watts. And then our P out is about 50 kilowatts. Okay? So how do we determine the gain? So this is gain is what we call the absolute value gain. Okay? Meaning, because it has the same unit, when you divide values having the same unit, they are actually cancelled out. Okay? So let's try to solve for number 1. So for number 1, again, in order to determine gain, it should be output over input. So in this case, our output is 140 volts. And then our input is 35 volts. So 140 divided by 35 would be around 4. So therefore, our gain is 4. So how would we know if our problem or the problem that we're trying to solve is gain or attenuation? We actually compare the output with the input. If the output is greater than the input, then it is gain. But if the value of the output is less than the input, then we call it as loss or attenuation. So let's box the answer. Again, when we talk about gain in absolute terms, when we define or when we divide output over input, it has no unit, or it is unitless. Okay? For number 2, we're trying to look for the gain for I in and this current. So I out would be 5 milliamperes. And the input is 20 milliamperes. Always remember, with gain, it's always output over input. Now, it might look a bit more complicated than the first example, as this one has a prefix of milli. Now, in dividing, or when you actually use arithmetic operations on prefixes, as long as they have the same prefix, you can actually directly solve for them. The only way or the only time that you'll need to convert them into its standard form is if those two units don't have the same prefix. So in this case, this has both volts. That's why we're able to divide them directly. This one has both milliamperes. That's why we're able to divide them. Okay? So 5 over 20. So 5 divided by 20 would be about 0.25. So our answer here would be 0.25. Now you might be asking, won't we be converting this into a standard or a engineering notation? Well, it is possible to put them into a scientific notation having multiples of 3, having 250 times 10 to the 3. But normally we only use prefix for values having units. But for unitless values like this, we usually tend to put it this way. Unless it's very, very large, or it's very, very small. In that case, we put it in scientific notation. Let's take a look at the last example. So this time it is power. The first one was voltage, the second one was current, and this last one right here is power. As always, A represents attenuation, gain, or amplification. For number 2, I forgot to mention, because you notice that this is 0.25, and we notice that the output is lesser than the input, then this is actually attenuation. Number 1 is gain, larger output compared to input. Number 2 has lower input compared to the lower output compared to the input, then this is attenuation. When we look at the gain in its absolute value, or its standard form, if the gain is greater than 1, we call it as amplification. If it's lesser than 1, or 1 to 0, or in between 0 to 1, then that would be a gain, attenuation or loss. So let's look at number 3. So this is the one that I was talking about. So output over input. So we will be having 50 kilowatts over 100 watts. Now, if you divide this directly, you'll be getting an incorrect answer. As remember, if they don't have the same prefix, we have to make sure that we convert this first into its standard notation. But of course, if you have your calculator with you and you know how to use it, you can just input this directly as 50 exponent 3 kilowatts divided by 100 watts. And the answer would be 500. Now, you will notice that this is above 1, so therefore, this is gain. One of the things that we have to remember that gain is usually shown through amplifiers. So in electronics, an amplifier, as the name suggests, amplifies voltage. It has a symbol of a triangle, almost like a buffer if you have studied logic circuits already. So normally in a schematic diagram, the gain is written here. For example, it is 500. Then you will see that it is written around 500 here to denote that this amplifier has an amplification of 500. Okay? So this would be the input, and this would be the output. Okay? Now, sometimes there are cases that the amplifier won't be able to give us the amplification we need. For example, we need an amplification of 30, but we only have amplifiers having amplifiers of 3 and 5 and 2. So what we can do is we can actually connect amplifiers in cascade. So meaning when we say cascaded, the output of the first amplifier is the input of the next amplifier. So for example, let's say this has a gain of 2, 5, and 3. So how do we determine the total amplification of these 3 cascaded amplifiers? So from the formula here, we can actually see that the total gain is just we multiply the gain of each and every amplifier. So A1 multiplied by A2 and A3. So in this case, in order to get total gain, it's just as easy as multiplying 2 with 5 and 3. So therefore, the total gain would be 30 in absolute terms. Okay? Now, oftentimes when we view an amplifier, or even when we look at mixers or anything to do with sound and anything to do with communications equipment, we won't be actually seeing gain and attenuation in absolute terms, but we would actually be seeing them represented as decibels. Okay? If you heard the term decibels, usually you will associate it with sound, as that is how they use the level of volume of a sound uh, compared to the smallest or the softest volume of sound that can be heard by a normal human being. So they compare it with that. I'm not entirely sure with the exact values, but this is how the way they convert it into decibels. The reason that they use decibels for conversion or convert terms like this into decibels, because there would be times that the gain in absolute terms would be very, very small, like, I don't know, 8 to 9 decimal digits, like 0.000000135, something like that. Or it would be very large, like around 3,900,000, something like to that extent. So it will be using lots of digits to represent it. Okay? So the same reason we actually convert values into engineering notation to shorten them or to be made easier to the eye, easily understood by someone who is looking at it, we also use decibels with the same regard. It's easier to look at decibels as any large values of number are actually shortened into 3 digits at the most. Okay? It is possible to get 4 digits, but that would require a very, very large number or a very, very small number. Same goes with decimal numbers that have multiple fractional digits in it. When if it has too many digits, converting it to decibels shortens it into around maximum of around 3 digits in decibels. Now, please take note of the following. How do we convert values into decibels? First, we get the absolute value, V out over V in, I out over I in, and P out over P in. The only thing that you have to remember is that after you get the V out over V in, we multiply it by 20 if the values that or if the gain that we're trying to convert into decibels is voltage gain or current gain. But if it is power gain, then we have to multiply it by 10. Again, if it's voltage or current, it has to be multiplied by 20 after finding the logarithm. If it is power, we only multiply it by 10. So if you have your calculator app with you or your physical calculator, how do we get or how do we do it in our calculator? Just a moment. Okay. So in this case, this is already in absolute value. This is the V out over V in already. So what do we do? So let's say the 4 is already there. So we just put in logarithm of 4 equal, then multiply it by 20. And then we get 12.04. So let's write it down. So that would be 20 logarithm of 140 divided by 35, which is already equal to 4. So how did I do it? Let's say we were using this, or we're using the initial given. So what we do is we get 140 divide. If you're not really used to putting all the quantities together in one computation, well, if you want to be careful, you can compute it one at a time. So 140 divided by 35, we have 4. Then we just click logarithm, log, of the answer. You get this, and then you multiply it finally with 20. Then you get 12.04. So again, we use 12 digits. Oops, I was trying to type it, but I just can put it here. 12.04. And this time around, it would have a unit, which is in decibels. Easy. Okay. Let's see. Let's put a box on this one. Okay. Next, let's have this one. So same. This would be 20 of logarithm of 5 milli over 20 milli. Now, again, if they have the same unit, it's okay to actually divide them directly. Okay. So if you want to put in the milli, that's fine. So let's say, for example, 5 exponent milli is negative 3 divided by 20 exponent negative 3. So we have 1/4, and we get the logarithm of 0.25, and then multiply it by 20. Now you'll notice that we get a negative answer, okay, which is actually the opposite or the negative value of the one that we have here. Well, that is because it is an attenuation or a loss. In decibels, losses are designated in negative decibels. Okay? So if it's positive, it is gain. If it is negative, it is loss. Now, number 3, you have to be careful when you do it in power, as you might have been used to using 20 as your multiplicand or factor. So 10, again, this is power. How do you know it's power? It says P and it is in watts. So 10, oops, where's my eraser? So logarithm of 50 kilowatts. This time around, we can't ignore the kilo and the unit because they are different. The one at the top is in kilowatts, the one at the bottom is watts. We got this already a while ago, 500. But I want to show you how we input it in the calculator as is. So 50 kilowatts is exponent 3 divided by 100 equal to 500, which is our answer a while ago. Get its logarithm and then multiply it by 10. So we get 26.99, almost 30, or almost 27 rather. So 26.99 in decibels. Okay. So we have two positive values in decibels. So these two are gain. So this one and this one are gain. While this one is attenuation because it is in negative. Attenuation or loss. How about in cascaded amplifiers? What if we have multiple amplifiers that are written in cascade? So let's have some triangles again here. Let's make them a bit larger than the last time. I don't know if this is larger. This just looks like longer, to be exact. And let's say we have the values of the gain here in decibels. Let's say this is 5 dB. Let's say this is 10 decibels. And let's say this is in, I don't know, 3 decibels. Okay? So how do we do this? Do we multiply them again? No. If it is in decibels, we have to make sure that if it is in absolute value, we multiply them to get the total gain. But if it is already in decibels, we only add them together. So meaning, if it's in decibels, that would be 5 dB plus 10 decibels plus 3 decibels. Okay? So the total would now be 18 decibels. Okay? So that would be our final answer. As part of your practice, I'll be giving you a few exercises and check and see if you are able to understand today's lesson. So let me give you 3 values. I want you to find their gain or loss in decibels. Okay. So let me just put in the value. Let's say okay. So Vin is 10 millivolts. So power input is around 5 kilowatts. Let's have the power output at 30 kilowatts. Number 3, let's have I in as 10 milliamperes and I out as 450 milliamps. Let us add a fourth example. I want you to get the total gain of this in decibels. So I have cascaded amplifiers, 3 of them. I want you to get their gain in decibels. Oops. Assume that this gain is power gain. Okay? So this is power gain. Okay? AP1. Let me write that. This is AP1. You cannot combine gain if they don't have the same unit. For example, if it's voltage and current, that is a no-go. Or voltage, it just must be all voltage, all power, or all current. So in this case, this is all power gain. This is in absolute value, not in decibels. Okay? What I need is the total gain in decibels. So make sure you do this and tell me how you fared. As always, anyways, thank you very much for listening to my lecture. Hopefully you already understood the importance of gains, attenuation, and decibels using engineering notation and frequency, wavelength, and bandwidth. Thank you very much for listening, and always stay safe and have a great day.